So these are the notes for learning target 2, the basics of the periodic table. First thing we need to look at is how the periodic table was arranged. So many years ago, when elements were first being discovered, we had the law of triads and the law of octaves, which grouped elements into groups of 3 as well as groups of 8. And then Dmitri Mendeleev arranged a periodic table, and he arranged them by increasing average atomic mass, which worked for most of the elements, but it didn't work for all of the elements. And then Moseley came along and he arranged it by increasing atomic number, which is the trend for the periodic table that we use for today. So the periodic table is called the periodic table because the rows of the elements are called periods. The columns, or the vertical groups that you see across the periodic table, are referred to as families or groups, and they get the name families because the elements that are in the same column or the same group tend to share some of the same chemical and physical properties. The periodic table can also be arranged into metals, nonmetals, and metalloids. The blue elements represent the metals, the yellow represent the nonmetals, and the pink are the semi-metals, also called metalloids. Notice that there are many more metals on the periodic table than there are the other two classifications. The different groups that I mentioned do have specific names. Group 1, excluding hydrogen, are referred to as the alkali metals. Group 2 is referred to as the alkaline earth metals. And they both have this root alkali in them because if they're mixed with water, they will form a basic solution, which is the meaning of alkali. Group 3 is the boron group. Group 4 is the carbon group. Group 5 is the nitrogen group. Group 6 is the oxygen group, and you will also hear this referred to as the chalcogens. Group 7 are the halogens, and Group 8 are the noble gases, and again, you will also hear those referred to as the inert gases. The transition metals make up the D block. The transition metals get their names because they can change oxidation states, or they can change their charges because they have a varying number of valence electrons. And then last but not least, you have the intertransition metals made up of the lanthanide and actinide series. You may also hear these referred to as the rare earth metals. Alright, so if you look at the noble gas configurations or the electron configurations for elements that are in a similar group or period, you do start to see some patterns. So within a group, calcium and strontium, for example, you see that they have different noble gases that they start with, but their valence electrons are going to be in the same type of sublevel. They're both in an S sublevel. They have the same number of valence electrons. However, they are in different energy levels. So calcium's valence electrons are in the 4th energy level and strontium's are in the 5th. Across a period, the configurations do start with the same noble gas, but you see that they have a different number of valence electrons. However, the valence electrons are found in the same energy level. So calcium has 2 valence electrons in the 4th energy level, and gallium has a total of 3 valence electrons in the 4th energy level. Remember, valence electrons are in the highest energy level present, so that's why we don't include the 3d electrons. So whenever you look at a square on the periodic table, you do find some useful information. You found the atomic number, that is a whole number, and that gives you the number of protons. You found the average atomic mass, remember that is a weighted mass of all of the isotopes of that element. And you also have the symbol, which is used worldwide. So it doesn't matter what country you're in, what language they're speaking, the symbols are going to be the same on the periodic table. And then if you're looking at a periodic table in an American classroom, you will see the American name of the element within the box. If you travel outside of the United States, those names may change, as a lot of countries outside of the United States still refer to the Latin names of the elements instead of a simplified or a different American name. For example, we would call element K potassium, but elsewhere in the world you would hear it referred to as kalium. So that's just one example. Sodium is called natrium. So if you're looking at a nutrition label, say in Italy or in Germany or somewhere, you would see kalium and natrium listed instead of potassium and sodium listed. Don't forget, there are 4 different blocks on the periodic table. You have the S block, which also includes helium, the D block, the F block, and the P block. We talked about those with the first learning target, but don't forget those for the second learning target as well. So on your note sheet, if you flip it to the back, we are going to take some additional notes on properties of metals, nonmetals, metalloids, and then we're going to look at some properties of specific groups. So properties of metals. Metals are malleable, okay, and as the picture suggests, you can hammer it flat into a sheet of metal. Okay. They are also ductile, which means that they can be pulled into a wire. They're also conductors. They can conduct heat and electricity. They are also lustrous, which means they are shiny. Okay. Most of them are solids at room temperature. There is one notable exception, and that is mercury. And they do have a smooth texture. Okay. Nonmetals. Nonmetals do not conduct. They don't conduct electricity. They do not conduct heat. That's why oftentimes nonmetals are used as insulators. They are not malleable. Most of them are very brittle, so if you hit them or strike them, they will shatter. They're not ductile. If you attempt to pull them into a wire, if you can even get that far, they will break. And they're not lustrous. They're not shiny. Most of them are dull. Although some of them do have some notable colors, especially the halogens and elements like sulfur, which is yellow, and carbon, which is black. Most of them are going to be brittle solids or gases at room temperature. Again, there is one exception, and that is bromine. Bromine is a liquid. Okay, you also have the semi-metals or the metalloids. Metalloids are found in between metals and nonmetals. They're kind of the boundary elements. They have the physical properties more like metals, so they're going to be lustrous. Some of them are going to be malleable, ductile. But whenever you look at their reactivity or their chemical properties, you're going to find that they react more like nonmetals. And then whenever you look at them and examine them on the atomic level, those atomic properties are going to be shared in between those of metals and nonmetals. Okay, and some additional information about each group or family. Okay, the alkali metals are found in group 1, as we said before. They all have one valence electron, and they are the most reactive metals on the table. If you see in this picture, all of them have to be stored in oil, and the reason they have to be stored in oil is because they are very reactive with water. They're so reactive with water that they can even react with humidity that's present in the air. If you want to see a video demonstrating how the different alkali metals react in water, you can go to youtube.com and you can type in the search bar Brainiacs Alkali Metals, and the first video that pops up should be just a really quick 3 or 4 minute video that demonstrates the reactivity of these different metals in water. It's quite interesting if you have the time to watch it. Group 2, these are the alkaline earth metals. They're going to have 2 valence electrons, and they're the second most reactive metal group on the table. Again, these will react with water, but not to the point that they have to be stored in oil. But they will oxidize very easily if they're left out exposed to the elements. Group 7, these are the halogens, and they're going to have 7 valence electrons. This is the most reactive group, hands down, metals or nonmetals on the periodic table. Halogens are also commonly used as disinfectants. Chlorine and bromine are most commonly used in pools and spas or hot tubs in order to sanitize the water. Chlorine is also used in municipal drinking supplies to remove contaminants. Iodine is used in medicine. Solid iodine is purple, but whenever it's mixed in solution or an alcohol solution, it turns an orangish brown color. So if you've ever had surgery or if you've ever donated blood, oftentimes your skin will be cleaned with iodine in order to disinfect the area, and it will stain your skin, so you'll have kind of an orangish, yellowy, brown color until the skin cells that have been stained die and are just sloughed off over time. The noble or inert gases are found in group 8, and these are going to have 8 valence electrons. There is an exception. The exception is hydrogen, or sorry, not hydrogen, helium. And why do you think helium would be the exception? Okay, well, remember, helium is found in the first energy level, and the first energy level is limited to s orbitals, and s orbitals can only hold a maximum of 2 electrons. So helium has a full valence shell with 2 electrons. So again, the noble gases typically have 8 valence electrons with the exception of helium, and it only has 2. And you've often heard that these are noble or inert gases because they do not react. Well, that's almost true. Okay, there are some exceptions. There are some times that they will react. Most notably, it will be the heavier noble gases, so those like krypton, xenon, and radon, and they're going to react with fluorine. And remember, fluorine is a member of the halogen family, and we said that the halogens are the most reactive elements on the periodic table, so it makes sense that if they were going to react with any element, it would be fluorine, a member of the halogen family. Okay, and then the valence number for each group, and if you're looking at the main group of elements, and if you hear someone refer to the main group elements, they are talking about the S and the P blocks. So if you number them all the way across and include every group, you end up with 1, 2, 13, 14, 15, 16, 17, and 18. However, if you just number the main group, group 13 is also group 3, 14 is also group 4, 15 is also group 5, and so on. And it just so happens that the valence number of electrons for each group corresponds to its group number. So group 1 has 1 valence electron, group 2 has 2, group 3 has 3, and so on. And hopefully you remember drawing these Lewis dot structures from middle school, but if you don't, you notice that all of the group 1 metals have 1 dot representing their 1 valence electron, and so forth. Remember that this doesn't mean that they only have 1 electron, it's just in their valence shell or their highest energy level, that's how many electrons there are. So this would be your first energy level, second energy level, third energy level, and so on. Okay, and that wraps it up for the notes for Learning Target 2. If you have any questions or if you're unsure of anything, you can go back and rewatch the video and just try pausing the video throughout. That way you have plenty of time to fill in your notes. If you still have additional questions, make sure that you ask one of your teachers for some additional help and clarification.